Bismillahirrahmanirrahim. Dear students, today we are going to start with our new sheet, which is the sheet 8, and it is about the performance measures here. Okay, so we wish to find that how efficiently our system is performing here. So basically, it's a very simple sheet which involves a set of uh, equations, or you can say set of formulas which you need to memorize only. Just before starting, quickly, just to review with you what exactly are the formulas we have here. The first one is the cycle time here. Cycle time means this is like your time period, means which is like the time between two consecutive rising edges or the falling edges of a periodic clock signal here. Okay, so I will be representing it as the CT here. The second one is the cycle count here. I will represent it using the CC here whenever we need it, and the cycle count is basically the number of clock cycles which we need or which we use for executing certain tasks here. Okay, next one is the cycle time we already discussed here, and then the clock frequency we have, or instead of clock frequency we will say that this is a clock rate here, like the frequency here. Okay, so I will be using F to represent the clock rate here, and this is basically equal to 1 divided by the cycle time here. Okay, like the you have already studied maybe in the signals, like frequency will be equal to 1 over time period here. So it's the same thing, the clock rate will be equal to 1 over cycle time here. Okay, I mean if you want you can remove these brackets here just to make it easy like this here. Okay, the next formula which we have is basically the CPU time here. Okay, it's like a lot of number of formulas here. Depending upon the information we are provided in a question, we can use it. So the CPU time is basically the time taken by a CPU in order to execute a job here. It's like the same as what we have in the cycle count, but in that case we are talking about the number of cycles for executing a task, and in case of the CPU time we are talking about the number of the time period or the time taken by a CPU to execute a job here. Okay, so this is basically equal to CPU time is basically equal to the cycle count multiplied by the cycle time here. I can also rewrite it as the cycle count divided by the clock rate here. Okay, so depending upon whatever information we are provided, we can use that one. The CPU time is also called as the execution time here. Okay, so depending upon the terminology used in the question, you can change it. Okay, like you instead of CPU time you can call it as the execution time here. Then the next one is the cycles per instruction here. Okay, so the cycles or clock cycles per instructions here, we can write it as the CPI here. Okay, so this is the number of clock cycles needed for a certain instruction here. So CPI will be equal to the cycle count divided by the instruction count here. Okay, and this is what we have, simple. Now we already said that the CPU time is basically equal to cycle count into CT here. So what we can do here, basically from here we can find the cycle count here. Okay, like this is basically your formula for the CPI here. Now just to have the multiple formulas for the CPU time, what we can do here, we can say that cycle time will be equal to the CPI multiplied by your instruction count here, and this information we can plug in here. Okay, so the second formula which we are getting here, like this was our first formula, this is the second formula, like the CPU time will become basically the CPI multiplied by the instruction count here multiplied by the cycle time here. We can also write it like this, maybe there's a third formula, the CPU time will be equal to CPI multiply by the instruction count. The cycle time is equal to 1 over clock rate here, so we can say this is our clock rate here. So this is like the three formulas we have here. Okay. Similarly, another formula which we have is the overall CPI here. Okay, so the overall CPI is equal to summation I equal to 1 to n here. We have the CPI of any instruction of type I multiplied by I of I. I of I is the number of times an instruction of type I came in a program or for certain task here, divided by the instruction count here. Okay, like I of I is basically the occurrence of an instruction of type I here. CPI means the cycles per instruction of the certain instruction I here, and instruction count will be the total number of instructions in a program here. Okay, so we will be also using this formula here. We also have another formula which is basically the MIPS here. This is basically millions instructions per second here. Okay, so uh, this is also like used to measure the performance or efficiency. Okay, like the execution time, you can also use the MIPS here. So MIPS will be equal to instruction count here divided by the execution time or the CPU time here. I'm just writing the execution time, the formula provided in your textbook here. This is also the CPU time, okay, into 10 raised to power 6 here. Another formula or the same formula which we can have is the clock rate divided by, we can have the CPI into 10 raised to power 6 here. Okay, so these are like the different formulas and the abbreviation which I will be following in this tutorial here. Cycle time, cycle count, clock rate, CPU time, multiple formulas we have, cycles per instruction, the overall CPI, and the MIPS. Okay, so this is the few formulas. These are the few formulas which I will be following for this particular tutorial sheet here. So let us start with our question one now. Now in the question one, basically he said that we are going to have a program. Like, let me read the question. Consider having a program that runs in 50 nanosecond on a computer A here, which has a 500 megahertz clock. We would like to run the same program on other machine B in 20 nanosecond. If B requires 2.5 times as many clock cycles as machine A for same program, what would be the clock rate of machine B in terms of megahertz here? Now, just to explain in another word, he said that we have basically a program here. Okay. Now, when we execute that program on machine A, it took 50 nanoseconds here. The machine A clock rate was 500 megahertz here. Now he said that we take the same program and we execute it on the machine B, and we want that it should take 20 nanoseconds on that machine A. Now he also gives you a hint that if the number of clock cycles, okay, like the cycle count for machine B is 2.5 times more than the machine A for certain program here, then what will be the clock rate of machine B in megahertz here? So let me write it in the terminology which we already discussed here. First of all, we said that the program is executed on machine A in 50 nanosecond here. So it means that the CPU time for machine A here. Okay, I'm just writing it like this here. It will be basically 50 nanosecond here. Okay, so which if you want you can say like 50 into 10 raised to power minus 9 second here. Similarly, the second one is like he said that the clock rate of machine A. So the clock rate of machine A, which will be f of A, is equal to f, okay, f of a. If you want, let me just to avoid confusion, let me make it in a subscript here. Let's suppose f of a here. Okay, this is 500 megahertz here, which is basically 500 into 10 raised to power 6 here, hertz here. Okay. Similarly, he said that the CPU time of machine B here is basically 20 nanosecond here, which will be 20 into 10 raised to power minus 9 second here. Now he said that the cycle count of machine B is basically equal to 2.5 times the cycle count of machine A here. Okay, this is what he has provided here. So we need to find what is the clock rate of machine B and megahertz here basically. Okay, now as we already discussed the formulas before, so you already know that the CPU time is basically equal to the cycle count divided by the clock rate here. Okay, because the CPU time is provided to me, the clock rate is provided to us, and the cycle count is somehow provided to us here. So now first of all, for f of b, so what we can do here, we can say that at f in case of b will be equal to the cycle count of b divided by the CPU time of b here. Okay, so basically what we have here, we need to find out what is the cycle count of B here. Okay, so we need to find out this term right now here using this formula here. So to find this one, we need the cycle count of A here. So to find cycle count of A, we will be using the same formula. So it means that we will be using the same formula which I have provided here. So it means the cycle count of A will be equal to the CPU time of A multiply by the clock rate of A here. Okay, multiply, not the convolution, just to avoid confusion. Let me make convolution, multiply here. So the CPU time of A is basically 50 into 10 raised to power minus 9 multiply by the clock rate of machine A is 500 into 10 raised to power 6 here. Okay, so this is basically equal to 25,000 into 10 raised to power minus 3, which will be equal to 25 cycles here. Okay, so since this is the cycle counts, it means the 25 cycles I get here. Now we already get the CCA of A here, so we can use this formula to calculate the SB here. So the clock rate of B will be equal to the cycle count of A, which is basically equal to 2.5 multiplied by the cycle count of A is 25 divided by the CPU time of B is 20 into 10 raised to power minus 9 here. Okay, so this is basically when you solve it, this will be equal to 3125 megahertz here. Okay, since this is what you need here. So this is your solution here. Let me write it here as FB here. So this is basically your required solution to this question. So basically, it was a very straightforward, simple question where we just used the formulas which we studied in the beginning of the tutorial here. Okay, now in the question 2, basically he said that suppose that we have two implementations of the same instruction set architecture here. So basically he said that we have two implementations here, okay, of the same instruction set. So it means the instruction set is common for two different implementations here. Now obviously one implementation is I think on machine A and the other one is on the machine B. So machine B has a clock cycle time. It means that the cycle time for machine A is 15 nanosecond and CPI is 4. Similarly for machine B, the clock cycle time, okay, this is time because this is in the seconds here, otherwise it will be in the cycles here. So this is clock cycle time is 55 for B and the CPI is 2.5. So now he said that which machine is faster and by how much here. So it means the information which is provided to us is the cycle time for machine A is basically 50 nanosecond here. If you want, you can convert it into 50 multiplied by 10 minus 9 here. Similarly, the CPI of machine A is 4 here. Similarly, the cycle time of machine B will be equal to 65 nanosecond here, and the CPI of machine B is 2.5 here. Okay, now the question is, which machine is faster? Which machine is faster? First thing this one, and then by how much here. Okay, so now first of all, what is the information provided to us? We have the cycle time, we have the CPI basically. Okay, so if you want to check which one is faster, we can check it by finding the execution time or the CPU time here. Okay, this is one of the metric here, because he did not mention which particular performance metric to use. So it means we can use it using the CPU time here. Okay, so in the CPU time, the formula which best suit is the CPU time for this particular question. Okay, because if you remember, we did multiple formulas for the CPU time here. So the CPU time is basically the instruction count. Okay, now for instruction I will write like this. Okay, directly only the instruction count multiplied by the CPI multiplied by the cycle time here. Okay, so if you remember from here, this two information is already given to you for both machines A and. The only thing missing here is the instruction count here. Now, in the beginning, I have already told you that basically I have two implementation, or you can say here, let me check. We have two implementations of the same instruction set here. So if the instruction set is same, it means the number of instruction is also going to be same here. So we assume the number of instruction to be n here. So assume, so we can, let me make it box here. So assume the instruction count to assume the instruction count okay, to be n for both machines here. So it means just I have defined a variable here, which is basically n, and can be any number here. Okay, so whatever the number is, I mean, it will affect equally for both machines here. So it means it is not going to affect our solution here. So let's suppose we say that it is n here. Okay, so then the CPU time or the execution time of machine A will be equal to n is the instruction count multiplied by the CPI is 4 multiplied by the cycle time is 50 nanosecond here. Okay, or you multiply by 10 minus 9 if you wish, no problem here. So this will be basically equal to power 200 and nanosecond here. Similarly, the CPU time for machine B here. So it is again n multiplied by, this is 2.5 multiplied by 65 nanosecond here. So which is basically equal to 162.5 n nanosecond here. Okay, so basically what happened, we have found the CPU time for two machines here. Now, because based on the CPU time, which machine is faster here? So it's quite straightforward from here. We can say that the CPU time is the time taken by any machine or taken by a CPU to execute some time here. So obviously, if the time taken is less for certain program, obviously that will be faster here. So in this case, machine B is taking less time to execute the same program than machine A here. So it means that the machine B is faster here. So we can say that since since let me clear since CPU time of machine B is less than the CPU time of machine A here. So it means machine or the CPU B, whatever is in the question, is faster here. So basically we have answered the first part here. Now by how much here? So for by how much, what we can do, we can find the ratio of the CPU time here. So we can say CPU time of B divided by the CPU time of A here, which will be basically equal to 162.5 and nanosecond will be cancelled. Obviously it's a ratio here. Similarly 200 n here. Okay, so n is again cancelled here, so it means it will be equal to the CPU time of B is equal to 0.8125 times the CPU time of A here. So I have basically written the ratio. So I mean, it's not must you should write B up and A down here. You can write it in terms of CPU time of A divided by the CPU time of B here. Importantly, while deriving the solution, what we will do, we will try to write a faster machine equal to some factor multiplied by the slower machine here. Okay, so it's up to you how you do it. Like it's a simple straightforward calculation here. So just basically what I follow is I write a faster up and the slower down here. But this is not a must here. You can write the slower up and faster down. But while you are simplifying, write like the faster machine equal to some factor multiplied by the slower machine here. Okay. So this was the solution to your part 2 here. Okay, and now let's start with the question 5. I'm going to just give you the hint about the question 3 and 4 here, and 6 also. Okay, so the question 5 basically, uh, what he said that consider the following performance measures were recorded when executing a set of benchmark program on machine A and B here. Okay, so I have two machines here and machine B here, and some benchmark programs values are being calculated based on certain instructions here. Okay, now the clock rate of a CPU is 200 megahertz, so it means he is considering a constant clock rate for both machines here. Now he said that which code sequence will execute faster according to MIPS and the execution time here. So we need to find out which code sequence is basically faster according to the MIPS here, as well as the execution time means according to the CPU time here. Okay, so now first of all, let us find that which code sequence will be faster here. Okay, so up to you. I mean, there are multiple ways to do it. Let us start here. In both cases, basically, we are going to find an overall CPI here. Okay, so first of all, we need to find the overall CPI. So I'm just starting from here. So you can say that the overall CPI of machine A here, okay, which will be equal to the summation, as I told you, n equal to I equal to from 1 to n here, and the CPI of I multiplied by I of I divided by the instruction count here. Okay, just ignore this one. This is not A. This is the general formula. Let's suppose we are going to use here. Now in this case, first of all, let's suppose we are going to have the CPI, the overall CPI of machine A here. So which will be equal to the CPI of instruction of type ALU multiplied by the occurrence of ALU here, plus then the CPI of the load. I'm just writing load and store, means this one here, load ls, I am just write load and store instruction multiplied by the occurrence of the load and store here, plus the CPI of the branch instruction multiplied by the occurrence of the branch here. I'm just using B for branch here. Okay, and plus the CPI of the other instruction multiplied by the occurrence of the other instruction here. Okay, now first of all, if you see here, if you observe here, basically number of cycles per instruction. So this is basically your CPI here, and this is the percentage of occurrence here. Okay, means this is the value of I, this is the I value here, and this is your CPI here. Okay, so now just simply substitute the value. Okay, sorry, divided by this all values divided by the instruction count here. Okay, so let us have substitute the value. So the CPI of ALU is basically 1 multiplied by the occurrence is 38 here. Okay, instead this is the percentage, so it will be occurrence here, plus the CPI of the LS is 3 multiplied by 15, plus the CPI of branch is 4 multiplied by the occurrence is 42, plus the CPI of other is basically 5 multiplied by the occurrence is 5 divided by the number of instructions here. So how many instructions do we have here? So we can find from here, like the in my program 38 instructions were basically ALU type here. Similarly 15 instructions were 38 instruction on ALU, 15 were the load and store, 42 were the branch, and 5 was the other instruction. And since this is basically the percentage, so obviously even if you add them, it will end up with 100 here. So I can write the instruction count as 100 here. Okay, so when you calculate the value here, the value which I obtained was 2.76 here. So this is basically the overall CPI of A. The CPI of a machine A is 2.76 here. Similarly, we can write the overall CPI of machine B here. Okay, I'm not writing the formula here, but it's all the same formula, but in terms of machine B here. So it means it will be basically the CPI for machine B will be 1 multiplied by 35 plus 2 multiplied by 30 plus 3 multiplied by 15 plus 5 multiplied by 20 here. Okay. And divided by, again, the instruction count in this case, since this is again a percentage here, so it should be 100 here. Okay, or you can do it here. 35 plus 30, 65 plus 15 will give me 80 plus 20 is 100 here. Okay, so when you find the value here, so the value which I obtained was 2.4 here. So the overall CPI for machine B is 2.4 here. Okay, now what we can do here, we can find the CPU time. Okay, he said which machine is faster according to MIPS. He is saying, okay, the first thing is MIPS here. Okay, so let's suppose first of all we need to find the machine which one is faster according to MIPS here. So if you remember, the formula for the MIPS was, just let me write here, the formula for the MIPS was the clock rate divided by the CPI multiplied by 10 power 6 here, or it was basically the second formula was instruction count divided by the execution time into 10 raised to power 6 here. Okay, so since right now what we have already calculated the CPI for both machines here. First thing, the clock rate is also given in the question, which is like 200 megahertz here, so I can go for the first formula here. You can use this one after you solve the execution time, which we will be doing in the part 2 here. Okay, so but anyone, you can use the same one, you should end up with the same answer here. So now the MIPS for A is according to million instruction per second. For machine A is the clock rate is 200 megahertz divided by the CPI of A, which was 2.76. We calculated just now into 10 raised to power 6 here. So this will cancel here. So 200 divided by 2.76 will be 72.46 here. Okay. Similarly, the millions of instruction per second for machine B is basically 200 into 10.6 into 10 power 6 here divided by 2.4 into 2.4 into 10 power 6 here. Okay, so this cancels out. So 200 divided by 2.4 will be equal to 83.33 here, if I'm not wrong here. Okay, let's cross check the calculation here. So basically what we got in this case, when we calculated the million instruction per second, we find out that basically the MIPS for A is 72 and the MIPS for B is 83 point something here. Okay. Now, since this is basically MIPS formula calculation, MIPS means the million instruction per second here. So the more instructions that are being executed in a second will be a faster machine here. So in this case, obviously, the machine B is executing more instruction here, or like let me write it like MIPS for millions of instruction per second for B is greater than the millions of instruction per second of A here. So it means, let me write here since, so machine B is faster here. Okay, according to MIPS here. Now, this was our first part here. Okay, now he needs to tell us which machine is faster according to execution time here. Okay, so we already know that the execution time, I mean, just let me write here, according to according according spelling. Okay, I wrote it wrongly, sorry. According to let's suppose execution time here. Okay, execution time here. Okay, or you can say this is basically the CPU time here. So now we know that the CPU time here is CPU time for machine A. Okay, we already know the formula here. It will be the instruction count here. Since this was in the percentage, so obviously this will be 100 here. Multiply by the CPI of machine A divided by the clock rate here. Okay, I'm just writing clock rate of A or B. In fact, it is same, so let me write it F here. Okay, so it's like common for both of them here. So we know that the instruction count was 100 multiplied by the CPI of A. This was the instruction count. Okay, this was the instruction count here. When you add all of them, this was the instruction count. And the CPI of A is 2.76 here. So 100 multiplied by 2.76 divided by clock rate is 200 into 10 raised to power 6 here. So when you solve it, I got basically 1.38 multiplied by 10 minus 6 here. Similarly, CPU time of B will be equal to, the instruction count is again 100 because this was the percentage here, multiplied by I think 2.4, which will the CPI of B divided by the clock rate is 200 megahertz here. So when you solve it, the value I got is 1.2 into 10 raised to power minus 6 here. So now, as you remember in the previous question, we found out that for the CPU time, in terms of the CPU time, the machine which takes less time to execute a task will be faster here. So obviously in this case, the CPU time of B is smaller than A is. So the CPU time of B is smaller than the CPU time of A is. So it means machine B is faster here again. And basically, I mean, what we find from this question is like if certain machine is faster according to MIPS, then that machine should also be faster in terms of the execution time because they are interlinked somehow. How it is interlinked? Because for example, if a machine B is faster according to MIPS, mean it is going to execute more instruction in per second, you can say. Then it means that if it is executing more instruction per second, so it means the execution time is going to be less for that particular machine also here. So that's why it should be faster also in terms of the CPU time or execution time here. Okay, so this was just a straightforward answer question here. Now what you can do basically, you can verify this MIPS using this formula also here. Instruction count is obviously 100. The execution time we already calculated here. This is the execution time here. Okay, into 10 raised to power 6. So when you solve it, you should be able to get the same answer which we obtained here. Okay, so depending upon like the main point in this all tutorial is depending upon the information provided to you in the question, you can basically use that information to solve it. Okay, so this is like what I wanted to tell you today, but let me quickly give you some hints. In fact, like the question 4 we already solved here. Let me write the question 4 here for you. Just give me 1 minute here. Okay, now this is the question 4 here. This is the question 4 here. Now, what he want here basically is the same question what we have here, but only for machine A here, which is a machine A here. This information is given to you. Okay. What we need to do here, he said that calculate the overall CPI here. So we have already calculated the overall CPI here. It's the same here. So you will get here the 2.76 for this particular question here. Okay. So basically the question 4 is already covered here. Okay. Now this is the question 3. I'm not solving it. In fact, just only I'm giving you the hint. Let me remove this one. Okay. What he said basically, he said that a compiler designer is trying to decide between two code sequences for a particular machine. So I have a single machine here, okay, and he's trying to decide about which code sequence he should use here. Okay, now as previously, what he did, the designer has supplied the following facts here. Now, as what we solved the question 5 recently, if you see here, I mean the instructions we were having, there was the ALU type instruction, branch instruction, load and store instruction were there, and the other instruction here. Okay, in this case, it did not specifically tell you which instruction we have, but rather he said that in the program, he has the instruction of type A here. It can be an instruction of type B and C here. It's like same, like for example, you can say A is basically branch, B is the load and store, C is basically your jump statement. Okay, so it can be any type of the instruction here. So he has just only mentioned A, B, and C here of certain type here. Okay, so next thing he said that the CPI of the instruction. So this is basically the CPI of instruction of type A, CPI of instruction of type B, CPI of instruction of type C. Now he said that for certain high level language, the compiler writer is considering two code sequence. So basically he want to decide about the two code sequences here. Now the code sequence 1, he said that the instruction count here. Okay, like this is basically the occurrence, like what you have occurrence previously. This is basically the occurrence, occurrence here. Like in the formula, this is the I here. This is the formula of CPI here. I means either it will be for A, B, or C. Same here. It will be for A, B, and C here. Okay. Now he said that the occurrence of A for code sequence 1 is 2 million here. Okay, because the values are in million here. So it means this is 2 here. So when you are writing it in the program, you need to write into 10 raised to power 6 here. Multiply by, for example, A, then plus B is 1 multiply by, 1 million multiply by 3 plus something like this. Okay, divided by the instruction count here. Clear? So this is what we have here. So you need to be careful about the million here. Okay. Next thing is the instruction count. So for a code sequence 1, the instruction count will be the addition of these all here. So for code sequence 1, the instruction count is basically 2 plus 1 plus 2 is 5 million here. So this will be your instruction count for 1 here. Similarly, instruction count for the code sequence 2. Okay, so these are like the small hints here. One more thing here. In this case, he has not provided any clock rate here. So what we can do, since he is considering the code sequence for a particular machine here, so we are going to use the same machine. So you can assume the clock rate as F here, as general here. Okay. So just you can solve using this one, like what we did previously with N here. So you need to find the overall CPI here. You know the formula, then which code sequence is faster here. Obviously, just you can use the CPU time here. I think here better. Even if you have the information for the MIPS, you can do that one also. And by how much is same, like then you can say CPU time of the one divided by the CPU time of two, assuming one is faster. Okay, I'm just giving you the hint here. So whichever is the faster, keep it up divided by the second one here. Okay, so this is how you are going to do the question number 3 here. The question number 6 is also similar here. This is your CPI, and this will be the value, mean the instruction count or the occurrence here. Okay, again it is will be 15 million here, 5 million here, 3 million here. So everything will be in terms of million here. So you need to find which will execute according to the MIPS as well as the execution time here, assuming the clock rate is 500 megahertz here. Okay, so we already solved the question number 3. It's more or less similar here. So I assume that you are going to try to solve this one, and if you face any problem, please you can discuss with me the solution here. Okay, again I'm not quite sure like if you have completed the performance, or you have started in the theoretical part. If you have not started, you can delay watching the session here. The session is already recorded for you, so whenever you finish with the theoretical part, you can watch it, so it will be more easy for you to understand it. Okay, and importantly, we are going to have quiz this week here, so please check the Blackboard announcement to find out. Okay, so thank you so much. Assalamu alaikum warahmatullahi wabarakatuh.